Hello students, welcome to EDAMIGO, an initiative by GATE ECE Top 3 Rankers. I welcome you all to the video lectures on previous year GATE questions on the subject Signals and Systems, Electronics and Communication, and the topic is Basics of Signals and Systems. In the video series, we are solving the questions and also analyzing the concepts on which the questions are based. So thoroughly we are going through the previous year questions. We have already covered part 7 of the topic basics of signals and systems, and this is part 8. So let's continue and let's go to the questions. So now let's start with the question. This is the first question, and here it is the relationship between output and input is given. Yt is the output and xt is the input. We have to find that is the system stable or unstable, time variant or time invariant. So we have to find this. Okay. So now first of all, let's solve for time invariant and time variant and time invariant. We know the method to check that the system is time variant or time invariant. Okay. Now, as we know that this is the relationship between output and input. Yt is the output and xt is the input. Okay. Now we can say that output t is equals to minus infinity to t input tau cos 3 tau d tau. Okay. So this is step 1. Now step 2, as we know, the step 2 is to find the delayed output, that is yt minus, for example, we will not use tau, we will use t naught. Okay, so we are shifting the output with the t naught. So in the whole expression, t will be replaced by t minus t naught. Okay. Okay, so this will be the expression of the delayed output. Okay, simply replace t by t minus t naught in the whole expression. Now step 3. Now to find the response of the delayed input, that is, we have to find the response of xt minus t naught. So input t is equals to xt minus t naught. Now using this relationship, that output is equal to minus infinity to t input tau cos 3 tau d tau. So we will replace t by tau and we will get that y dash t, that is the response, is equals to minus infinity to t x tau minus t naught cos 3 tau d tau. Okay. Now if we replace, let alpha is equals to tau minus t naught, so d alpha is equals to d tau. So y dash t is equals to minus infinity to t minus t naught x alpha cos of 3 alpha plus t naught d alpha. Now if we see that this is the response of the delayed input and this is the delayed output. Okay, and we can see that if this is equation number 1, this is equation number 2, they are not similar. Okay, so we can say that yt minus t naught is not equal to y dash t. So the system is time varying. Okay, so the system is time varying. Now to check the stability, to check stability of the system, we know that we check BIBO stability, okay? And to prove that system is unstable, we only need one bounded input, okay? We only need to prove that output is unbounded for any single bounded input. So we have to find only a single bounded input for which the output is unbounded, and if this is the case, then the system becomes unstable, okay? So the general rule that we have seen in the previous case is that if xt is equals to un or xn is equals to xt is equals to ut and xn is equals to un is given as input and the output is unbounded, then the system becomes unstable. But if in this case we see that yt is equals to minus infinity to t x tau cos of 3 tau d tau, if we give input as ut, then we can see that the system will come out to be stable. But if we give xt is equals to cos of 3t, and we know that this is a bounded input, okay, so this is a special case where for this single bounded input, so this is a bounded input, and we will see that yt will be equal to minus infinity to t cos square 3 tau d tau, and we can see that this will be an unstable or unbounded output, okay? So for this particular input we can see that the output is unbounded. So for this particular bounded input, output is unbounded, and thus the system is unstable, okay? Unstable system, okay? So we can say that it is a time varying and unstable, okay? So it is non-time invariant and non-stable. So D is a correct answer to the question. Now let's look at another question. So it is given that yn is equals to hn convolve gn hn is equals to 1 upon 2 to power un, and gn is a causal signal. If y0 is 1, y1 is half, then g1 is equal to, okay? So we have to find g1, okay? So gn is a causal signal given to us. Gn is a causal signal. So we can say that gn is equals to 0. Gn is equals to 0 for n less than 0, okay? So let us say that gn has values g0, g1, g2 and so on, okay? So this is at location 0. So if we convolve yn is equals to hn convolve gn, so the convolution, as we know that, we will write it like this: h0, h1, h2 and so on, g0, g1, g2 and so on, and we will multiply them, and the first term will give me y0, the second term will give me y1 and so on, okay? Now we will write the values. As we know, hn is equals to 1 upon 2 to power n un. So the values will be 1, 0.5, 0.25 and so on. G0 we don't know, G1 we have to find, G2 we also don't know. Now we will multiply them, and we can see that when you multiply G0 with 1, we get G0, 0.5 G0, 0.25 G0. Then we'll put a cross sign. We'll get G1, 0.5 G1, 0.25 G1, and then double cross, and then we will get G2, 0.5 G2, and so on. And for G3 we will put 3 cross. Okay, and for other terms also we will put cross here, and we can see that this is Y0 and this is Y1. Now since in this column all the other terms will be cross, so we can say that, and in this column also all the terms will be cross only, so we can say that Y0 is equals to G0 and Y1 is equals to G1 plus 0.5 G0. Okay, now there is an information given in the question that Y0 is 1 and Y1 is half. Okay, so Y0 is equals to G0 is equals to 1. This implies G0 is equals to 1. Y1 is equals to G1 plus 0.5 G0 is equal to half. Now as G0 is equals to 1, putting the value of G0, we can say that G1 plus half is equals to half. So G1 is equals to 0. So we get the value of G1 by simple convolution, and we can say that the answer is A, that is the value of G1 is equals to 0. Now let's solve this question. It's a very simple question. It is given that Hn is equals to 2 to power n u of n minus 2, and it's a LTI system. Okay, whenever we have to define the properties of a system using impulse response, then the system has to be LTI system. Okay, now as we know that for LTI system, the condition of causality, the condition that the system should be causal is that Hn should be 0 for n less than 0, and for stability the condition is that summation of mod of Hn for n equals to minus infinity to infinity should be less than infinity. Okay, so these are the conditions. Now as we can see that Hn is equals to 2 to power n u of n minus 2, so this signal will start, or we can say that this is equal to 0 for n less than 2 and is equals to 2 to power n for n greater than equal to 2. Okay, so we can say that this Hn is equals to 0 for n less than 0 also. So Hn is equal to 0 for n less than 0, and it is satisfying the condition of causality, so the system is causal. Okay, now let's check the stability. As we know, the condition of stability is that Hn should be absolutely summable. Now here, to check stability, now here as we know that Hn is equals to 2 to power n u of n minus 2. So if we plot Hn, so we can see that it will start from 2. So it will be 2 to power 2, that is 4, 2 to power 3, that is 8, 2 to power 4, that is 16, 2 to power 5, that is 32, and so on. And we can see that Hn is a rising signal. Okay, so it will not be absolutely summable, and thus it will not satisfy this condition, and that's why it will be an unstable system. Okay, so this will be a unstable system, and that's why the answer to this question is it is a causal but not stable. So B is a correct answer to the question. So thank you, students. We will be continuing solving the questions of the same topic in the next part of the lecture series. So keep sharing these lectures, subscribe to the channel, and give us the feedback. Thank you.